because we're going to talk about implicit differentiation today. This is a new process, really important process. Once you click all those Chromebooks closed, new process in calculus for us that's very, very useful. It's not like we're doing anything. We already have all the pieces to do this. We just haven't put this together as a process. So first of all, before we talk about implicit differentiation, let's just define what do we mean by implicit versus explicit, because to this point everything we've done has been an explicit process. I haven't said those words, but now we need to, because we're going to do something different. So implicit means this: an algebraic function is explicit when the dependent variable, typically y for us, not always though, is written, expressed strictly in terms of the independent variable, typically x. So another way of saying that is the equation is written with y isolated. The y appears one time on the left side of the equation and everything else is on the other side. Okay, that's an explicit process. That's normal for us, right? Implicit, on the other hand, an implicit function is one that is not and frequently cannot be written as one variable in terms of another variable. So in other words, y is not isolated in the equation and frequently appears in multiple terms. Okay? So now let's compare the two a little bit, and we can kind of work into this new process of doing differentiation in a way that leverages this blue concept instead of the yellow one, which oftentimes is much, much easier to deal with. Okay, and I will put these notes up. I know I haven't been great about that, but today I'll get these notes up. So they'll be on, this PDF will be available this evening on Planbook. Okay, let's look at a couple quick examples. Well, the top one, that's old news, right? That's an explicit derivative. We've done stuff like that already. What is the derivative? What's dy dx if y equals x squared? 2x, sure. And we're just, we're differentiating, and we get 2x. By the chain rule, this is not necessary to write, but if we were to follow the chain rule here, there's really only one layer to that, right? But if we think about this as something squared, well, the derivative of something squared is 2 times something times the derivative of what's inside, the derivative of x with respect to x, which is what? 1. Yeah, so we don't ever write that, do we? We just write that as 2x. If we're differentiating, if the variable in the expression we're differentiating is the same as the variable of differentiation, right? You get what I mean when I say the variable of differentiation. The variable of differentiation is x in this case, because I'm differentiating with respect to x, right? I'm differentiating something, d something dx. Okay, when those two match up, when the something I'm differentiating is a function of the variable of differentiation, well, the chain rule is always unnecessary. The last step would always be 1, right? So we don't even write it. Okay, that's different than that example. Okay, now we're differentiating z with respect to t. What's the variable of differentiation here? T. Okay, give me 1 to 5 on that. Everybody get that? The variable of differentiation is t, right? Okay, I mean, seriously though, because that sometimes people, they don't understand what I mean when I say the variable of differentiation is t. Does a t show up in our expression? So is the chain rule essential? Yeah, right? Because though I'm not differentiating with respect to t but the function is not a function of t, and I'm differentiating with respect to t, I'm going to need that extra link in the chain rule, aren't I? Right? So how would I do this problem then? This is a weird one. We haven't done one like this yet, but we can. What is dz dt? Well, what kind of rule am I going to have to apply to take that derivative? Okay, but at the outside, isn't that a product? Everybody see what I mean by that? If I look at that, that's a product of two factors, isn't it? So I'm going to have to differentiate this with the product rule. Okay, so help me out. What am I going to get? Okay, so first is x times the derivative of the second, right? Okay, what's the derivative of y squared with respect to t? Well, what's the derivative of hand squared? 2 times hand, right? Well, hand is y this time. So I'm getting 2y, but I'm going to need another link, aren't I? Because this is a y and that's a t. So hand is a y. Well, what's the derivative of y with respect to t? dy dt, right? Everybody see that? Okay. So there's half of the product rule. I got x times the derivative of y squared, okay? Plus, now we're going to flip it around. So now I've got the second factor times the derivative of the first. Well, what's the derivative of x with respect to t? dx dt. It's not 1, is it? It's dx dt. So we could call those, we know that we're differentiating with respect to t, so we could call those primes if we wanted to. We could maybe simplify this and write this as 2xy y prime plus y squared x prime, where we know we're differentiating with respect to t, so the primes refer to derivatives with respect to t. Okay, now give me 1 to 5 on this. How are we doing? Okay, let's try, should we do one more like that? That'd be good? Okay, let's try another one. Let me make one up here. So how about if we let's try one like this. What if y Okay, I'm gonna try one like this. What if we do y? No, I don't want to do that. Let's do z equals x squared sine y. Okay, let's calculate dz dt. Okay, Pagan, help me out. What rule am I going to apply first here? It's product, yeah, because I've got an x squared times a sine y, right? Okay, so help me out with that. Product rule. You do the first half. X squared times the derivative of the other part, right? So what's that going to be? What's the derivative of sine hand? Cosine hand, right? So the first link in the chain is going to be cosine of hand, which is a y. Now we're differentiating with respect to t here, right? So what's the second link going to be? What's the derivative of hand with respect to t? Hand is a y, so what's the derivative of y with respect to t? dy dt, right? Now let's so we're going to get a dy dt there. Let's compare that right over here on the other side of the board. I need a little more room, don't I? A little more room. Let's compare that to a different problem. What if we had z equals x squared sine t, okay? And I did dz dt. Well, that's still a product, right? And the first layer would have been x squared times the derivative of sine t. What's the derivative of sine t with respect to t? Cosine t End of story, right? That's it. We would have just gotten cosine t times what's inside the sine t. P dt is 1, so I don't even write it. You see the difference here, right? Why did we need that extra derivative here and not here? Well, because here, sine was a function of y, not t. So I've got that extra link that's imposed by the chain rule, okay? Okay, let's finish the job here then. So what's the second part of this one gonna be? What do you think here? Dilute, what's the second part by the chain rule gonna be? So we did first times derivative of the second. Now we have to do, okay, sine y, second times 2x. So first of all, we've got the derivative of hand squared, right? Because we got, it is gonna be 2 hand, right? Okay, so we're gonna get, okay, but once we peel away hand squared, what's inside is not a t. So what do I also have to include? Dx dt, right? Okay. So we end up then with dz dt is equal to x squared cosine y times y prime, right? Y prime is just dy dt plus 2x sine y times x prime. Okay? All right, so let's take a slightly different look at this now. We're gonna approach the same concept from a different direction. Let's warm up with a problem that we already know how to do. So we want to find the tangent line to that curve when x equals 3. So to come up with a equation of a line, we need a point and a slope, right? Okay. You need me to go back, Becca? Okay. So we need a point and a slope. So how am I going to get my point? Plug it in. I'm just going to plug x equals 3 into my function to find the other half of that ordered pair, right? So we get the ordered pair x equals 3, y equals what? 9. Okay? We need a slope. How am I going to get the slope? Got to find the derivative, right? That's the job of a derivative. So this is an easy one. I'm differentiating with respect to x, right? Everybody get that? So this is an easy derivative, normal derivative. What is the derivative of x squared with respect to x? 2x. So what's the slope of our tangent line then? 6. Yeah, because all I'm doing is plugging 3 in for x, right? So I'm getting 6, and this is easy. Now I just use point slope. Y minus 9 equals 6 times the quantity x minus 3, right? And we got it. And we could clean that up if we want to. You know, we could rewrite that in slope-intercept form if we want to. That's fine. And this is what we've done. Okay, we just found the slope of the tangent line at that point, and this is what the line looks like, maybe. Right? That's bad line. You get the idea. There's my tangent line. Okay, that's the equation of that tangent line. Give me 1 to 5. How we doing? Okay, that's all good, right? That's stuff we've been doing. Not a big deal. Okay, this is a little trickier. What makes this one a little tougher? The y is being squared. Is this an explicit equation or not? Okay, but is it now? No, right? Is the y isolated? Thumbs up or down? Thumbs down. It's not. It's inside a squared function, right? For y to be isolated, it has to be written as y equals, and that's not what's written. It's y squared equals, right? Okay, so if I wanted to come up with a tangent line when x equals 9, what am I going to do? Okay, square root both sides. And that's going to give me something like that, y equals the square root of x. Okay, make sense? Okay, y equals the square root of x. And so now we could plug in x equals 9 and get what for our ordered pair? Well, if I plug 9 in for x, the square root of 9 is 3, isn't it? So I get my point of tangency. I've got my new function here. I've got my new function y equals the square root of x, which is just x to the 1/2. So what's y prime equal to? 1/2 x to the negative 1/2, which is the same as 1 over 2 times the square root of x. So what's the slope of my tangent line then when x is 9? Right? 1/6, right? That's good, isn't it? 1 over 2 times the square root of 9, it's 1 over 2 times 3, so 1/6. Okay. So we got the equation of the line. Y minus 3 equals 1/6 times x, the quantity x minus 9. And so if I were to, let's clean this one up. If I distribute the 1/6, then add 3 to both sides, you get 3/2 plus 6. So what is that going to be? 9/2. So I get y equals 1/6 x plus 3/2, right? There's the equation of that tangent line. Something like that. I didn't draw it very well, but it's going to go through 1.5 evidently. If I did my math right, I could have messed it up, but you get the idea, right? Okay, everybody happy with that? I'm not. I don't think that's right. Partially right.
Wouldn't you have plus or minus?
Yeah, you would, wouldn't you? Right? Now the math gods, again, we're always discovering a new appreciation for those math gods. They're so clever. When you solve that equation, y squared equals x, you get two different answers, don't you? You get y equals plus or minus. That or is important. Plus or minus the square root of x, right? So in reality, what this graph should look like is that, right? Now, or is an important word here because if I take those as separate pieces, each of them is a function on its own. Whereas the overall graph clearly violates the vertical line test, right? So this relation, y squared equals x, is not a function of x, right? It's not because it violates the vertical line test. But when you ask the math gods what you get when you solve for y, and they reply, y equals plus or minus the square root of x, they're giving you the answers as the two possible functions that you would build to create that single graph. You get the red positive square root of x and the green negative square root of x. But as you can see, there are two different tangent lines when x equals 9. We only got one of them, right? We'd have to go back down here and do that same process for the other half of this function, right? Everybody see that? We'll go through and kind of organize our work in a second. Okay, that worked, right? We were able to solve for y here and build multiple functions, and still we're going to be able to come up with both of the equations of the tangent lines, right? It's going to take a little bit of work, but we can get there. Okay, I want to compare that to that yellow example. Y e to the x equals log y squared. Okay, that's going to be tougher. Isolating y there is going to be tough to do. Might even be impossible, right? So our strategy is going to probably fail on that one. So we got to find something better. Okay, again, let's what did we just do, right? We solved this thing up here. We said y equals plus or minus the square root of x. And if we take y equals positive the square root of x on one side and y equals negative the square root of x on the other side, we ought to be able to work our way down and find those tangent lines. Okay, so we already did the work on this one. We calculated y prime and got 1 over 2 times the square root of x. And so we ended up then with, we were able to plug in, we had the point over here, 9, 3, and this gave us the slope of the tangent line was 1/6, right? That's all the information we extracted from our function and its derivative. Let's do the same thing over here. What would this derivative be? Only difference is that negative sign out front, right? So if I'm differentiating negative the square root of x, I could pull that negative out front and differentiate the square root of x and then multiply by the negative again, right? So what's the answer going to be? Yeah, negative 1 over 2 times the square root of x, right? So what's that give us for our points then? Well, if I plug 9 in for x, I'm going to get negative 3 for y, aren't I? I get negative the square root of 9, which is negative 3. And the slope of my tangent line is just going to be negative 1/6, right? And so we end up getting, what did we come up with for our tangent line? We got y minus 3 equals 1/6 times x minus 9 over here. And on this side, y minus negative 3, wrong color, y minus negative 3, so y plus 3 equals negative 1/6 times x minus 9. And if we do all the math here, I'm going to get y equals negative 1/6 x minus 3/2, and y equals positive 1/6 x plus 3/2. Okay, good? All right, let's see if we can come up with a better approach, though. So what if I take all this stuff right here, I'm going to take a picture. Could we come up with a more efficient way than having to do this explicit process the whole time? What do you think the answer is? I bet we can. Okay, so there's everything we did. Let's cover up that stuff so that doesn't. Okay. Let's try doing this a different way. Let's try using an implicit process. Okay, so we're starting with the equation, y squared equals x. What if we just differentiated each side with respect to x? Okay, so I'm going to take the derivative with respect to x of y squared on the left side and the derivative with respect to x of x on the right side. Right side's easy. What's the derivative of x with respect to x? 1, right? Okay, what's the derivative of y squared with respect to x? Okay, so the first layer is the derivative of hand squared is 2 hand, right? Okay, so I'm getting 2y times, new color here, we'll go with that color, times what's the derivative of y with respect to x? dy dx, right? Which we'll just call y prime, how about? Okay, because that's what we called it before, right? I think we did. Yeah, we called it y prime over here, didn't we? That's just dy dx. Okay, on the other side, the derivative of x with respect to x is 1. Well, what if I solve for y there, or y prime? What do I get? Y prime is equal to 1 over 2y. Okay. Isn't that really what we got over here if we rearrange this stuff a little bit? Let's take this equation right there. Let's take a little closer look at that. Y prime equals 1 over 2 times the square root of x. Well, what's the square root of x equal to in the red equation that we started with? Yeah, that's how we defined y, isn't it? Right? So that's the same thing as saying y prime equals 1 over 2y based on how we defined y at the start of that explicit process, right? Okay, what about over here? Let's take this one and let's just rearrange that a little bit. That negative could be out front, it could be in the top, it could be in the bottom, right? There's just a negative somewhere. One of those factors, 1, 2, or the square root of x, needs to be negative to make the whole fraction negative, right? Why don't we rewrite it this way? How did we define y in the green function? Negative the square root of x. So what do you know? We also get y prime equals 1 over 2y if we define it that way. Okay, so we didn't even need to do that stuff because we got to that same result much more quickly here, didn't we? Right? Everybody see that? Okay, we got y prime equals 1 over 2y. So if we take a second look at this then, if we use our implicit process and we calculate y prime, well, let's repeat that process again. We need practice anyway. So on the left side, if we differentiate with respect to x, we get 2y, y prime. On the right side, if I take the derivative with respect to x, we get 1. And so our derivative, again, y prime was just 1 over 2y. Well, look, we have 2 points on our relation y squared equals x, because that's the graph of the whole relation y squared equals x, isn't it? Right? It's a non-function. But there are 2 places where x is equal to 9. What if we take the top one? If we take this point right here, we end up with y prime equals 1 over 2 times, well, what's my y value here? 3. It's 1/6. That looks familiar, right? How about down here if we take this one? If we take this point, we get y prime equals 1 over 2 times, what's my y value here? -3. So -1/6. What do you know? We got those results much, much more quickly using this implicit process, didn't we? Right? Everybody see that? Way better. Way better. Okay, we had to do quite a bit of work over here to come up with those, the slope of the tangent line, and that was a bit of a process. But the points, from this point on, everything's the same. We have the slope of the tangent line, we have a point, we have the slope of the tangent line, we have a point slope, and we're done. Right? It's just that here we get those derivatives much more easily. Well, there are the points, the x and y values. Okay? Give me 1 to 5. Is that making sense? Okay, what we're doing here? I mean, at first I wouldn't expect many, if any, 5s, but they'll get there. Okay, let's try another one. But let's abandon completely this idea of trying to solve for y. We don't need to do that. We're just going to implicitly differentiate with respect to x. If we want y primes, y prime is going to be dy dx, right? We're trying to find the slope, right? dy dx. Well, how am I going to get y primes out of this? I'm going to differentiate with respect to x. So I eventually, when I differentiate a term with y's in it with respect to x, at the end of the chain rule process, we can already anticipate I'm going to get a y prime there, aren't I? Right? So if we do this, if we differentiate with respect to x implicitly, what's this first term going to give me on the left side? What's the derivative of x squared if I'm differentiating with respect to x? 2x, right? No big deal. 2x. Okay, what's the derivative of y squared if I'm differentiating with respect to x? 2y, y prime. There you go. So we're seeing a pattern already, right? Every time I've got a term with y's in it and I differentiate, I should expect to get y primes popping out by the chain rule. On the other side, what's the derivative of 4 with respect to anything? 0. Okay. Well, that's easy enough now, right? We can solve that for y prime. We could divide by 2 and just get rid of those. So y prime then is equal to what if I isolate y prime? Everybody agree? Negative x over y, subtract the x to the other side, divide by y. Okay. So if we wanted to find y prime when x equals 1, what are we going to do? Okay, when x equals 1, I'm going to go back to my original equation, and I'm going to plug 1 in for x. Well, that's going to give me 1 plus y squared equals 4. There are 2 different y values, aren't there? I'm going to have to solve for y. When x is 1, what are the corresponding values of y? Well, to solve for y there, but this is different, isn't it? Now I'm solving explicitly for y in terms of numbers, not other variables. That's easy, right? It's much, much tougher to solve for y in terms of other variables, right? Okay, so I'm going to subtract the 1 to the other side. Y squared equals 3. So what does y equal in this case? Okay, but plus or minus, right? Because I'm square rooting both sides of the equation. So y equals plus or minus the square root of 3. So I'm getting 2 answers then. I'm getting one answer where y equals 3, and I'm getting another one over here where y equals negative 3. If y equals 3, and we already know x is 1, well, what's y prime equal to then? Y prime equals negative 1 over 3, right? How about over here? What if y equals negative 3? Then y prime equals negative 1 over y, which is negative 3. So y prime equals positive 1/3. And we can see that here, right? On our unit circle, this is not a unit circle, on our circle, and that's what this equation is, isn't it? X squared plus y squared equals 2 squared. So it's actually a graph of a circle with radius 2. Yes? The square, where's their, oh, you're right. Ha, you square root. You're right. Yep. That's supposed to be a square root of 3. There we go. Right. And this was going to be, yep, you're right. Sorry about that. Let's go back and fix that. So we get negative, oops, gotta get my pen. Negative x, which is 1, over y, which is negative the square root of 3. Well, negative 1 over negative the square root of 3 is positive 1 over the square root of 3, right? So I get 2 different answers depending on which point we're using, right? Because when x equals 1, look, we're going by halves there, right? So x equals 1, is that line. Right, I get 2 points, one there with coordinates 1 square root of 3. And I get one down here with coordinates 1 negative the square root of 3. And I get 2 different values for the derivative then, don't I? Right? I get this line up here. That's bad color. Let's go on that one. I get that tangent line. What's the slope of that one? That one is negative. That's this guy, isn't it? Right? That's the slope of that one up there is negative 1 over the square root of 3. And I get this positive one, or this tangent line with a positive slope down there, where m equals positive 1 over the square root of 3. Okay? That's a lot of stuff we got with a pretty simple derivative process, right? The derivative didn't take us long at all. That's it right there. Everything else was just using the derivative to find values. Okay? Let's try another one. A little tougher one. Okay? But it's really not that bad, right? How many y primes are we going to get in our equation when we implicitly differentiate with respect to x? I'm going to get 3. How do you know? Because there's 3 terms that have y primes in them. Okay? And then we're just going to have to just do some algebra, solve for y prime, right? Gather the y primes on one side, y prime terms, factor out a y prime. We're just going to isolate the y prime, but that's just algebra, right? You guys are going to get, I know that's, you're going to be so good at algebra here by the end of the year. It's just going to be laughable. When you get to college, you'll have it. So what about this first term then? What's that going to give us when we differentiate? And what are we doing here? Let's be really clear about this. The process we're doing is we're going to differentiate. How would I describe this? You guys tell me. What am I going to do to get to the next step? Differentiate with respect to x. And I'm even going to say, add one word there. I'm going to differentiate implicitly with x. Okay? I'm differentiating, meaning I'm just going to go through and differentiate term by x and see what happens. So what do I get from, first one's easy. That one we could have done weeks ago. What's the derivative of 2x squared with respect to x? 4x. No big deal. Okay, what about this guy? Now this guy here, let's break that up into a product. And rather than pulling the 3 out in front and redistributing, this is my bias. I always just lump the constant with one of the factors. And then we can eventually factor all that stuff out if we want to. So let's think about this as being a 3x times a y squared and apply the product rule. So what's that going to give us, Tori? We got a product rule problem here. So, okay, so we're going to do first times derivative of the second. What's the derivative of y squared with respect to x?
2y dy.
Okay, good. So we're going to get 2y. I'm going to call it y prime. I urge you to call it y prime because it gets really visually messy when you start adding a bunch of dy dx's in there, right? It's a lot easier and cleaner if you just call it a y prime. Okay, well, there's one y prime because we had a y in that term. Let's keep going. Let's try to kind of keep track of these. So that stuff gave me, we're not done yet though, are we? Plus, what else are we getting from that? That's only half of the product rule. What's the other half going to be? We did first times the derivative of the second, so now what? Okay, what's that going to be, Becca? Plus, yeah, exactly. It's going to be y squared times 3, and we'll just plug that 3 out front, won't we? Right? Okay, so there's everything we get from the second term. Now we're going to subtract whatever we get from, let's kind of divide that up like that. We get a 2x squared and a y, how about? So I'm going to put brackets here because we're subtracting whatever the product rule gives us for the third term, right? Jonathan, help me out.
4x.
Okay. Okay, well, let's, just so we're consistent, let's do first times the derivative of the second plus second. You don't have to, but just so we're doing it the same way every time. So 2x squared times derivative, but we're differentiating with respect to x. So y prime, there you go, good. Okay, so we get a 2x squared, there's our first factor, times the derivative of the second. The derivative of y with respect to x is y prime, okay? Plus, Liliana, second part of that, we did first times derivative of the second, so now we got to flip that around. Y, good, times, what's the derivative of 2x squared? 4x, there you go. Good. So now we're on to the last term. The derivative of 4y cubed. Well, that's not even a product rule issue there, is it? Right? That one's pretty straightforward. Let's see. So the derivative of 4y cubed with respect to x. What do you think? Okay, so the first layer is going to be, if we're doing the derivative of hand cubed, we're going to get 3. You're right. So 3 times hand squared. Well, 3 times 4 is 12. Good. So we're going to get a 12y squared, right? But we got one more layer to that. We're differentiating with respect to x. So what's going to pop out? Y prime. There you go. And that's all equal to the derivative of 10, which is 0. Okay, so we're out of here in 1 minute, right? Okay, so I will finish this up tomorrow, and then I'll let you finish the test up, okay? But do you see at this point, we're done with the calculus. Right now all we have to do is just isolate the y prime, and that's it. So what's that going to amount to? We're going to gather all of the y prime terms on one side of the equation, push all the other terms to the other side, factor out a y prime, and divide away whatever's left behind, right? So we'll watch that. It's no big deal. Okay.